Hello everyone. Once again, welcome you all to the 11th week lecture of this course, Fluid Dynamics for Astrophysics. So, as we see in previous 2 or 3 classes, we have shifted to MHD from the basic hydrodynamics or fluid dynamics. So, we have now introduced the presence of magnetic field and how it changes the plasma dynamics. In today's class we will move on to the wave studies. So as I was discussing in the last 1 or 2 minutes in the previous class, that there are 3 types of basically, if we consider the homogeneous plasma medium, then we can have 3 types of MHD waves. So they have different characteristics, and the observation of them will have different uh, evidence observationally. So in today's class we will discuss about different kind of waves and how we can detect them in case of sun, which is one of the natural laboratory available to us to study the plasma dynamics. So I am SRIPAN and I am working as a PMRF at ITBHU, and this lecture series is one of the deliverables of my candidature towards the continuation of PMRF fellowship. So now let's move on to the first question here. So choose the correct statements regarding the sound waves. So as we discussed also that what is a sound wave. So sound wave is basically a longitudinal wave which moves through the elastic medium, and due to the presence of elasticity, and how it moves is like longitudinally. So that means there is rarefaction compression along the propagation of the wave, right? So now the question is how do we generate it? So if you follow the classes given by faculty in this for this course, you will find out that to generate any waves we are going to give some velocity perturbations, right? So initially we are considering that there is a background in which you don't have any velocity, and also the other parameters in the plasma dynamics like pressure, density, temperature, those are remaining fixed until and unless there is some perturbation in the system, right? Now if you have the velocity perturbation, and if we consider that okay, these perturbations are relatively small, that means their amplitudes are such that they cannot be changed to shock waves which will be present in the nonlinear regime. So now let's say you have perturbed the velocity, that means you have given some initial velocity to the medium which is in equilibrium otherwise. So now how the wave is going to generate, right? So when you are giving a velocity perturbation, and so what happens is it is a longitudinal wave, so the wave propagation vector that is perpendicular to the direction of the velocity perturbation, which is not correct, right? So wave propagation vector is along the direction of velocity perturbations. So how do you define it is let's say, if you recall that how this equation has been written like rho dv dt equals to minus grad of p plus rho g, and there can be that Lorentz force, right? This is the momentum equation in MHD, and there can be another, let's say, other terms which are unknown. So let's say f u, right? So now when you are considering the sound wave, you are basically considering the hydrodynamics. So then what happens is This hydrodynamic or the sound wave is due to the pressure gradient basically. Okay. Now if you have you can find out one you know the so the sound wave is basically a compressional wave. So for compressional wave, what you have is this divergence of V, right? So since this is compressional, so this divergence of V should not be 0, right? So it should not be 0. That means now you have V has, let's say V is given by some parameter V0, and then you have exponential, right, I, let's say omega t minus kx, right? So this is the case. So you can find out that there will be an equation which is like k dot v, right? That should be equals to, sorry, not equals to 0. So you can find out that for compressional wave you should not have k and v which are perpendicular to each other. Okay, so it should not be the correct option. First one is not a correct option. Now the wave propagation vector is along the direction of velocity perturbations, which is correct. Okay, now the group and phase velocities of small amplitude sound waves depend upon the sound frequency. How do you know that? Is omega square equals to cs square and then k square. Okay, so your so your phase velocity, which is omega by k, which is cs, right? And if you do d omega, omega equals to cs k, so you have cs and dk, right? So you have I think I am making some mistake. So you have d omega dk, that is also we have cs, right? So group and phase velocities of waves depend upon the sound frequency. Is it? So it is not, because you don't have any omega or k dependence in the sound speeds, right? So the group and phase velocities of small amplitude sound waves do not depend on the sound frequency. This is one of the correct answer, and this one is correct, but this one is not correct. Okay, so this is for sound waves. Now how sound waves are propagating is, let's say you have a magnetic medium, for example. So these are, let's say, your magnetic fields, right? The sound wave propagates in this direction without perturbing the magnetic field. It will perturb only the plasma. So let's say you have some denser compressed medium here, extended medium here, and then you have denser compressive medium here. Okay, so this way it will perturb plasma only, but it will not perturb the magnetic field as it propagates towards the through the medium. Okay, so this is the discussion about the first problem which we have. Okay, so yeah, now the next question here is about the sound speed. So sound speed depend on temperature as 166 T naught to the power half m meter per second inverse. So what we know is the sound speed is given by gamma p by rho, right? And then we know p equals to what? Rho r, t r, right? So if we write it like this, so you will find out that you have gamma t R, right, or gamma kt by m. So from using the 5 by 3 and the value of R and those things, you can find out that it will be like proportional to root over T. Fine. Now you have to calculate the speeds of acoustic waves in the photospheric level and outer atmosphere of the sun. So first of all, what is the structure of the sun, right? So we know the sun is the star which is giving us the light, right? And so what happens in sun is it has a core which is which has high temperature, and because there is nuclear fusion going on in which hydrogen is converted into helium. So now if we recall the blackbody radiations concept, so we assume that if the energy source is at the source is at the center of some object, if we go far from the object, we will find out the temperature will decrease as the distance is increasing, right? So now what happens is in sun there is, let's say this is a photosphere, so up to this level you have this one is 10 to the power, let's say 7 Kelvin, and in photosphere it is around 600 Kelvin. But then you have corona, which is the outer atmosphere of the sun, and surprisingly it has a temperature of 10 to the power 6 Kelvin. Now this is a big question mark which is for research community who are working in solar physics. Okay, so this is majorly known as coronal heating problem. So this is not exactly the black body concept. There should be many other things which are to be investigated in this about this problem, right? So now, okay, let us assume that these values are correct, and with this we can find out the acoustic speeds. So now we have to calculate it, right? So let's say we are telling that okay, Cs at, let's say, photosphere, which will be around 166, and then root over a 6000 meter second inverse. So if we try to find out it, so it will give you a value of, let's say, 1288, sorry, it's not 8, 12858 meter give me some second, I think, yeah, so this is meter per second. So you will find out that if you go to meter to kilometer, it will be around 13 kilometer per second inverse, right? So around that. Now eventually if you go to corona, let's say Cs at C, let's say corona, so 166, then 10 to power 6 meter second inverse. So 10 to the power 6 is it will be around 166 into 10 cube, right? So this will be meter per second inverse. So you should have basically 166 kilometer serpentine bus. Okay, this is your answers. For corona, you will find out the sound speed has to be higher because corona has higher temperature than the photosphere. Okay, so fine. Now let's move on to the next question. So now we have a question regarding alpine speed. So in alpine speed, we have a formula like VA equals to this. So how do we feel it? So what we know is about VA is you have B by root over mu and then rho, right? So now rho can be changed by like mass of proton or let's say electron, the total mass, which is can be given as the hydrogen itself. So rho can be like rho can be written as like n by m h, right? So using those things you can find out this formula, right? Okay, here fine. Now you have a coronal region just above active region. Okay, so in a photospheric network region, so you have this one. Fine. So if we have to find out the ratio of alpine speed in these two regions, so let's say this is VA, which is around this is around, let's say AR, which is C, basically coronal regions, and VA is around network. So you should have like B naught at AR by B naught at, let's say, n for network, and then you have just a second. Yeah. Okay. So yeah, n naught by, sorry, this should not be the same here. So it's like n naught at n by n naught at here, right? And this is spin under the okay. So now you have here, you should not change, you don't need to change it to the Tesla, because you are basically taking the ratio. So 1000 by 100, so 100 by 1000, and then in network region it is around 10 to the power 23, and here it is 10 to the power 16, that is around half, right? So this is 1 by 10, right? And you have 10 to the power 7 by 2 per 7 by 2, that means you have 10 to the power 5 by 2. Okay, so this will be the ratio of alpine speeds in these two regions. Okay, so you see it depends upon both, like what is your background density and what is your background field, not on the one than the other. So it depends upon both. If in some region, let's say you have less density but you have higher magnetic field, and you have on another place in which you have higher density but you have lower magnetic field, they can have similar kind of alpine speed, right? But in this case, since we have the other option, like you have magnetic field is small, and also your density is also small, and in other case your magnetic field is strong and also density is strong. So you'll find out that there is some difference between the Alfvén speed in these two given regions. Okay, so now if we move on to this question, there is a movie here. So the question is, which kind of disturbance is this one? So first of all, let us recall what are the properties of this different kind of waves. So slow magnetoacoustic wave, it is a compressible kind of wave. That means it can perturb the density, and if you perturb the density, and what this is a image from SDO EIA, which basically is a spacecraft which is capturing the different layers of the solar atmosphere, and these are basically some intensity images. Now intensity image depends upon the density itself. So if there is slow magnetoacoustic wave, it will perturb the density and it can be captured by the intensity images, right? Now if we consider the Alfvén wave, you know it is an incompressible wave. So that means any propagation of Alfvén wave cannot have any signature in the intensity image, since it does not perturb your density. Okay, so since this is a intensity image, okay, imaging, so you cannot trace the presence of Alfvén wave from this. Now we have two options left. Okay, so Alfvén wave can be discarded because we cannot trace it from intensity images as it is incompressible, that is does not perturb density, right? Okay, so we can discard Alfvén wave. Now we have two options, which is slow magnetoacoustic wave and fast magnetosonic wave, right? So let us recall about these two also. So if you have slow magnetoacoustic wave, what happens is it can perturb your plasma but not the magnetic fields, and it will move along the magnetic field itself, since this is a longitudinal mode. And fast magnetosonic wave, it will have larger speeds and it can move isotropically and across the field line itself. In both these cases, you can have compressibility there. That means you can trace them in intensity images, both slow and fast. Now the question is, how can we differentiate between these two waves? So for slow waves you will find out the propagation direction along some magnetic fields, but and it can have some anisotropy associated with it because it has a certain directionality in which it is moving. But if you find that there is some perturbations in the intensity images which are let's say isotropic, or let's say going across the magnetic field structures, you can term it like a fast magnetosonic waves rather than slow magnetosonic waves. Now if we look at this particular movie, you can find out that there is some wave trends are going, and now here also, here you have some wave trends, right, and which are moving. You can see here also these are some wave trends, and you can find out another thing. This is a image in which you are finding that some bright and dark fringes are going around. That can have a possible structure of like rarefaction or compression, right, which is one of the observational evidence of acoustic modes, right. So let's say here you can find out these wave fronts which are basically moving across the field lines. Since if it is moving along the field lines, it should not have this circular wavefront like structures. It can have like a let's say it can move along the field lines itself, but here this is across the field lines, so we can tell that this is a fast magnetosonic wave. Okay, so this is a fast magnetosonic waves. Okay, so okay, fine. Now let us move on to the next question, which is about this one. So this is another animation or movie, what you can say. So first of all, let me give you overview of how these images are. What is this image? So this is not an intensity image, this is a velocity image. Okay, you know about the Doppler velocity, a redshift and blue shift, right? So redshift means it is going far from our eyesight, and blue shift means it is coming towards our eyesight. Okay, now these are some particular regions in the solar atmosphere, let's say on disk, and you can see that there is some blue shifting followed by red shifting. You can find out a bundle of field lines here, and it is changing from blue to red, right? So one particular line in this case is going from red to blue and then blue to red, this repeatedly, right? So that means you have a bundle of field lines which is going in this direction and then in this direction, right? So that means you have a torsion kind of thing, like you have done the experiment of torsional pendulum. What you do is you rotate it like this, and then it keeps derotate, and then again it's rotate, right? So in this way, now you are seeing this plane, you are not seeing the 3D. So if you are seeing this plane, so you will find out that sometimes the field lines are going away from you, so that means it will be creating the red shift in the Doppler images, which are this, and then it comes back towards you, so that will give you the blue shift, right? So which we are seeing here, one particular field line is going to red shift and then it's coming back to blue shift, so that means you have some torsion kind of thing. Now this is okay. So another thing is, as I discussed before, that this is a Dopplerogram, but now if we have intensity image, should we should we have this image? So one is alpine waves. Now alpine waves have pure mode, which is incompressible, so it should not have any signature. But in case of torsional alpine wave, we may track it in intensity images also, but this it's better to look at the Dopplerogram. It will give you the idea of this back and forth motion along your line of sight, so that can be a signature of a torsional alpine wave. Okay, so this is basically a signature of torsional alpine waves. Okay, so fine. Now we can have the next question. So we have consider two systems A and B. The magnetic pressure in A is twice the magnetic pressure in B. Now the density and temperature in A and B are same. Choose the correct options. So how do we find out about the alpine speed? So you have alpine speed, which is PA, and that depends upon like B by root over mu and then rho, right? Rho. So you have PA, and which is A, let's say, and you have PA, which is, let's say, for B. Now you have magnetic pressure. You have magnetic pressure, so let's say P for pressure B. Okay, this is for A, this is twice 2 PB for B, right? Now the magnetic pressure depends upon this B squared by 2 mu, right? So I am not going to do that. So B square, now here it is 2 B square at B, right? So this BA, which is this, that is equals to root 2 B. Okay, so you have this one. So you have B A by B. So that is equals to root over T. So alpine speed of system A will be root 2 times of that in B. Okay, so E is correct. Now these two are not correct. Now the last one is the sound speeds in A and B will be equal. Now our concern is what we are taking. We have the sound speed, which is root over gamma P by rho, right? So it depends upon, also it can be depend upon that root T, which is temperature, right? So here the dense temperature in A and B are the same, so sound speed in A and B will be equal. Okay, so this is correct answer. Fine. Okay, now if we go back to the next question, so choose the correct statements. So slow magnetosonic waves become almost isotropic when the alpine speed is much larger than the sound speed. Slow magnetosonic wave cannot be isotropic. It should have some anisotropy. It will propagate along the magnetic field, so it is not isotropic irrespective of the irrespective of the values of Alpine speed and the sound speed. So first one is not a correct answer. Now when Cs is greater than Pa, the slow microsonic waves propagate at a speed that is greater than Pa and smaller than Cs. So slow microsonic waves can have a speed which is at most Cs. It should not exceed the value of Cs, and it should not be greater than Pa itself. Okay. Now, when Cs is greater than Pa, slow magnetosonic waves propagate at a speed that is smaller than Pa. Is it true? So, obviously, you have the slow magnetosonic waves which will propagate at a speed that is smaller than Pa. Okay, fine. When Cs is less than Pa, now this time you have Cs which is less than Pa, so waves propagate at a speed that is smaller than Cs. Fine. Okay. So whatever the smaller speed in between Cs and Pa, slow magnetosonic waves can have a speed which is smaller than the smallest of the Cs and Pa. Okay. So here the answers are C and D. Okay, so C, this is D. Fine. So, okay. New slide. You have insert option here. So this one is there. Okay. Now the next question is, now we are moving towards shock. So shock is basically a discontinuity in the different parameters like magnetic field, density, velocity, these ones. Now for MHD shocks, the mass fluxes on either side of the shock will be equal. That is the truth, right? Mass flux will be equal. Magnetic stress needs to be taken into account in considering the conservation of momentum flux. Yeah, so when there is no magnetic field, we should not stress about the magnetic stress. But here you have a magnetic stress, right, which is depending on the J cross B term. You should take it in account when you are considering the MHD shocks and when you are considering the difference in the properties in the shocked and unshocked region. Now the pre-shock mass flux will be larger than the post-shock mass flux, which is not true. Total mass flux remains constant. Pre-shock momentum flux will be smaller than post-shock momentum flux, which is also not true because momentum flux is also remain constant around or across the shock. Okay, so this one is for A and B. Okay, so fine. Okay, so we have another question here. So give me just 1 or 2 minutes. Okay, so we have the last question for today's class. So choose the correct options. So for a first mode oblique MHD shock, what does it mean by oblique MHD shock? That means it is not moving towards the or along the magnetic field, and it is not moving in let's say perpendicular direction, it is in between that. So B field is attracted towards the shock normal. So we have fast mode, we have slow mode. For a slow mode oblique shock MHD shocks, the B field is attracted towards the shock normal, and then you have the other things are the component of B magnetic field perpendicular to the shock surface does not suffer a discontinuity. For the first mode oblique shock, the B is conserved across the shock. So for a fast mode oblique MHD shock, what happens is the B field is refracted away from the shock normal. Okay, so the first one, this one is not correct. It is not towards, it is the away, right? Away from. Okay, now for the slow mode shock, oblique shock, so B field is refracted towards the shock normal. So this one is correct. Now the component of B magnetic field, which is perpendicular to the shock surface, does not suffer a discontinuity. So now we know this, that the component which will be perpendicular to the shock surface, it will not suffer a discontinuity. Okay, this one is correct. Now for a fast mode oblique shock, the magnitude of the magnetic field is conserved across the shock. So for a fast mode shock, what happens is the magnitude of the magnetic field increases in the aftershock region. Okay, so this is increases in after shock region. Okay, so this one is done. So in today's class, what we have discussed is about waves, and then we move on to MHD shocks. So we have started the MHD, and then we discussed the basics. Now coming to the perturbation, which are small in amplitude, and that will gives rise to some waves phenomena, right? And then if the amplitude is higher, then we will find out the shocks, and we understand some properties of unshocked and shocked region, how the parameters are going to change, or whether there is any change in the mass flux, momentum flux, and what are the other extra terms which we need to incorporate in our equations, in which when the magnetic field itself is present, right? So we have discussed about the observational evidence of different kind of waves, like torsional alpine wave and fast magnetosonic waves, how they are going to be observed in solar atmosphere, which is one of the best laboratory we have to understand different kind of plasma dynamics in embedded in magnetic field. Now we will move on to the resistive regime in the next class, which will be the last class for this course, in which we will discuss about the magnetic reconnection. So okay, Okay, fine. So we started with ideal MHD. Now we will go to restive MHD. So I hope now the message is clear that when you are starting MHD, you will have some basic assumptions, like the length scale in which we are considering the plasma dynamics will be higher, much higher than the dpi length scale, because up to dpi length scale you will have the misbalance or misbalance of the charge neutrality. That means you cannot consider it to be charge neutral or quasi neutral. So beyond the length scale of dpi length scale, you will have the liberty to find out the quasi neutrality. Okay, so also there is a temporal scale which will be higher than uh, the inverse gyro frequency, right? So these are two length scales or time scales which we need to find out whether they are following the criteria for the MHD scales. And in MHD scales also we are trying to find out the fluid description instead of the particle interactions. That means we are going to macroscopic scaling, where in which we are considering only the bulk uh, output, right, instead of individual particles interactions. So then we find out some basic equations in which we have the mass continuity momentum equation, in which we saw that it depends upon the pressure gradient, it depends upon the gravity force, and also now since we are in MHD, it depends upon the Lorentz force. Now Lorentz force will have two terms, one is the magnetic pressure and another one is the magnetic tension, right? So then we saw that okay, if the magnetic field lines are somewhere more let's say concentrated than the other region, then there can be some misbalance in the magnetic pressure, and that can give us the magnetic pressure from the high to low pressure region, right? And if there is some curvature presence in the magnetic field, that means you have some change in the magnetic field along the magnetic field itself, that can give you the magnetic tension, which will act to restore the straightness of the field lines, right? So then we move on to the sound speed and alpha speed, and you see that when you consider the sound speed, you need to consider the temperature, and depending on the temperature the sound speed will be changing. And also we have a surprise element here, that as you go further from the photosphere, you are finding out that the temperature of the outer layers of the solar atmosphere is higher than that in the photosphere, which is not expected from your black body radiation spectrum, right? So there is so much something more about the solar atmosphere. There might be some energy transport or mass transport which we don't know from our undergrad classes, right? So that gives you some problem like coronal heating problem, which may be introduced in some more advanced methods. And then we find out the Alfvén speed, and we find out that it depends upon the background magnetic field and also on the background density itself. It's not only the magnetic field or not only the density, it depends upon both, and depending upon the contribution from both, the Alfvén speed will be calculated, right? Then we went to the this things. Alright, where we consider that okay, so you have some observation. Now Alfvén wave is an incompressible wave, so it should not disturb your density structure. And since in intensity images taken from the spacecrafts, which are imaging spacecrafts, you should not trace the presence of Alfvén wave, because it is not going to part of density. That means your intensity images should not trace it, or should not have any trace of the of the alpine wave. Rather, you should have a slow or fast mode of magnetosonic waves, because those are compressible and those can be traced from the intercepting images. Now, when you consider the slow or fast wave, we should have one thing is like the propagation speeds, which we may let's say estimate. But the another thing is slow magnetosonic wave is basically a anisotropic wave, which basically moves along the field lines. But in case of fast magnetosonic wave, it should have an isotropic property. It can move across the magnetic field itself. So in this case, in this movie, we have shown that this is the case, like fast magnetosonic wave. And then we have another movie in which we have the Doppler image, this time the velocity image, and you will find out the line of sight propagation, and that is due to the torsional alpine waves, which is analogous to a torsional pendulum experiment here, right? So you have blue and red shift repeatedly, that gives you this motion, right? So then we move on to some alpine wave calculation, and then yeah, so then okay, to go to MHD shocks, we will find out some other uh, properties of the shock and unshocked regions. Now we have wave study, we have covered wave, we have covered shocks. Now we will go to the restive MHD, in which we will be talking about the magnetic diffusion, which is the, let's say, your magnetic Reynolds number will be less than 1, because your diffusion property is more important than your magnetic advection. Okay, so one of the consequence of your magnetic diffusions is the magnetic reconnection, in which okay, we will discuss it in the later class. So thank you very much for attending